Hello, in this video we introduce a very important conic section known as a degenerate circle. Just kidding, an ellipse. Let's get started. So recall that if we had a double cone and we sliced that double cone with another plane, like a piece of paper, at various angles, we formed different types of conic sections. In previous videos we've talked about the parabola and we've talked about the circle. Today we look at the one in the first picture here that is at this slanted angle called an ellipse. So let's take a look at what the equations of an ellipse would look like. So we see here in our picture on the right of our screen that we have two different orientations for an ellipse. So like I mentioned earlier at the beginning, a circle was the set of all points which are the same distance away from the same fixed point in the center, and that distance is called our radius. The reason I joke about calling an ellipse a degenerate circle is because rather than going the same radius, like 3 units up, right, left, and down from the center, we would go maybe 3 units left and right, but maybe 4 units up and down. So we would not have a perfect circle. We would have something called an ellipse. The two types of possibilities are that our ellipse is more horizontal or more vertical, and we see that in our first picture here. So if we take a look at the picture on the left side of your screen here in the box, we have a situation where we have a horizontal major axis. And what we mean by that is that the actual longest side is the left and right side from the center, and the shorter side is going up and down. And we have the vertical major axis, similarly, with the picture that is drawn on the right. So what I wanted to point out here, first of all, before we jump in to the actual definition of what makes an ellipse, what makes this trajectory elliptical in nature and not parabolic or circular, we're going to start by defining some terms. The first term I want to define is this letter A. And so you see in the box below the picture, it says what A, B, and C stand for. So when we say the letter A, lowercase a, we mean the distance from your center to each of the vertices on your major axis. Remember that major just means longer for ellipses. So what we're saying here is, for example, if your center was at the origin, at the point 0, 0, then if I went A units from that point to the left, or A units from that point to the right, we would get the two locations of our vertices. For example, I could call this like vertex 1 and vertex 2. And those are both the same distance away from the center, and that distance is A. So it could be 5 units, for example. 5 to the left, 5 to the right. That's what we call A. When we talk about B, on the other hand, that's going to be a smaller number. So for example, if A was 5, maybe B is 4. 4 will be the distance, in this case, or B will be the distance, from your center to an end point on the minor axis, which means just the smaller axis here. So our smaller axis. So again, A is your longer distance from the center to each of your vertices on the major axis. This is an example of a horizontal major axis, but had it been vertical, A would have been the distance from the center to this vertex and from the center to this vertex. So that would have been A units long here and A units long there. So we can see that that's what we mean by A. But what we mean by B is a smaller number that takes you from the center to an end point on the minor axis in both directions from the center. So we now know that A is always bigger than B when we're talking about an ellipse because we have a degenerate circle. If A were equal to B, then the radius would be the same in all 4 directions, and this would be a circle. There's one other letter, though, that we need to make note of because we're about to formally define what we mean by an elliptical trajectory. And that letter is the letter C. So let's talk about what that C stands for. The C is actually this smaller distance than A that is going to be inside of your elliptical trajectory. It's actually fundamental in the design. So for example, if C was right here, that distance from the center to a fixed point, or maybe it's over here, the distance from the center to a fixed point. And again, there are 2 of them, so it's focus 1 and focus 2. In plural form, we usually say foci. Some people say foci. I just think that sounds silly. So I'll be saying foci for the plural of focus 1 and focus 2. So I'll say here, this is, let me grab my pen, right there. Okay, so this point would be like focus 1, and over here you'd have another one that's C units away, and that would be called focus 2. So again, focus 1, and the same distance C away from the center, there's focus 2. Okay, so what are these foci and why do we care about them? Well, it turns out that the formal definition of an ellipse is such that if you were to have a center in between your vertices on your major axis, directly in the middle, and you were to actually want to draw this trajectory perfectly, you would need two fixed points, which are c units away from the center, called the foci. Think of them like toothpicks. In fact, you can click on the toothpick video at the bottom of your slide here and watch a nice example of someone creating a perfect ellipse using these toothpicks and a string. So if we were to go ahead and have those two fixed points called our foci, and we were to then measure the distance, let's pick any point on the trajectory. I'll pick this point here, for example. If this is truly a point on my trajectory of my ellipse, then if I were to measure the distance to one fixed point and to the other fixed point and add those distances up. So let's say, for example, that the first distance was 2 units and the second distance was 8 units. Then if you add those two distances, you get 10, right? Turns out, if this is truly a point on the pathway, then if I picked another point, maybe up here, and I were to measure the distance from that point to the first fixed point, and maybe I get 1 now, and then from that point to the other fixed point, I would be guaranteed to get 9 there. And that's because the sum of those distances, and we have our note right here, the sum of the distances to those two fixed points called foci should remain constant. That's what we mean definitionally by being on an elliptical path. If you were to measure the distance from any point on your trajectory to both of those fixed points called the foci, which were c units away from the center, the sum of those distances better remain constant. If they don't, they're not truly points on your path. So that's what we mean by an elliptical trajectory. There's a formal definition involving foci. Okay, a couple of other things to fill in your notes here. If you're tracking with me so far, I may have lost all of you, but we'll see how many of you survived the video. The next thing I want to notice is, what is the length of my major axis? So if I take a look here, the major axis was our longer axis. So if I knew that the distance from, let me get some space here so I'll clean up here. The distance from my center to my vertices, if I knew that distance was a units long, so from here to here we said was a units long. If we know that fun fact, then how long is the entire axis, the major axis? Well, wouldn't it be a plus another a, which is a total of 2a? So 2a should always be the length of your major axis because it goes a in each direction from the center. Similarly, if I said what is the length of your minor axis, you would use the same logic. If you went b units from the center to this endpoint on the minor axis, then you'd have to go b units the other way to get to the other endpoint on the minor axis, just like if you were doing a circle, but now it's our degenerate circle known as an ellipse. So in that situation, what did we end up with? A length of, that's right, 2b. So you can fill in your notes there. The length of your major axis should always be twice a, the length of your minor axis should always be twice b, and a should always be bigger than b in an ellipse. If they are equal, what is it called? A circle, right? Now, one other note before we jump into the equations of the ellipse, which is in that blue box on the left. There is a special relationship that has been discovered for any elliptical trajectory, okay? And that relationship is between the letters A, B, and C. Now, what you're about to see on the screen, or maybe you've already looked ahead, is something that might remind you of the distance formula, or really the Pythagorean theorem, where you have a right triangle with sides A, B, longest side C. You remember that a squared plus b squared equals c squared. Well, in this situation, we see that c squared equals a squared minus b squared. That minus sign can throw students off. They weren't expecting that. But if you actually look at the ebook or the hard copy of our textbook, you'll notice a proof in there that actually shows you that when you actually use the distance formula in a couple of interesting ways, getting the distance from your foci to your fixed point on the actual trajectory and to your other foci, using the distance formula a couple of times and solving for c, this is what ends up happening. C squared will equal a squared minus b squared. Another way I like to remember that when I first learned about these as a student was because I knew that a had to be bigger than c in the definition here of the picture, since a is the distance from the center to the vertices and c is inside of the ellipse. I knew that minus made more sense. Subtracting makes more sense because that would reduce the size between a squared and b squared rather than increasing it with addition. So this actually will make intuitive sense as you get into your problems. Now, as we jump into the equations, before you get overwhelmed, I wanted to start with something that you actually believe already, okay? So let's take a look at the equation of a circle for a second, since ellipses are just degenerate circles, right? Let's look at a circle whose center is 0, 0, so that would be x squared plus y squared, and let's say that the radius was, how about 5? So 5 squared would be 25, wouldn't it? That would have been the equation of a circle centered at the origin with radius 5. Now, technically, I could have written this a different way. I could have gotten a 1 on the right side of the equation. How would I have done that? That's right, I could have divided every term by 25, by that number. And if I did that, then I hope what you'll see is something that looks like one of our standard forms of an ellipse in the boxes to your left. Because what we have here now is x squared over 25 plus y squared over 25, and we just have it equaling 1, which is quite nice. Now that looks like the standard form of an ellipse. But the reason that it doesn't quite fit the bill is because in the ellipse, A is supposed to be bigger than B. But in this case, A and B are both going to be 5. Because in our formula, A squared and B squared go in the denominators, don't they? So in this case, A equals B, and they're both equal to 5. That's why this is not an ellipse, but a circle, okay? But I point that out because by telling where the bigger number is, where A squared is versus B squared, we know what kind of major axis our ellipse will have. For example, if the bigger number is under the x being squared, then we're going to have a horizontal major axis. But if the bigger number A squared is under the y term that's being squared, we're going to have a vertical major axis. So for example, let me just write one up real quick and see if you can determine which one it is. If I had x squared over 16 plus y squared over 36 equals 1, could you tell me what type of major axis that ellipse would have? Right, its center is the origin. Its bigger number is 36 underneath the y squared term. So this would mean that we would have a vertical major axis. And we'll be doing some graphing of these in the next few examples, but the basic idea is you want to look for where the bigger number is. If it's under the y term, we'll be going up and down longer than we would be going left and right. And if it was under the x term, then we'd have a horizontal major axis rather than a vertical one. Okay, that was a lot of content. So at this point, I would recommend pause, make sure your notes are really clean, make sure you understand the concept of what an ellipse is and what each of these definitions stand for, and then jump into your next example with me. Let's see here, clean that up. Okay, in example 1 here, we're going to ask you to find the foci and the vertices of an ellipse, and we've described the ellipse a little bit for you. We've said that the center of this ellipse is at the origin, 0, 0. What I would always recommend to students is to draw a little sketch of what's going on. So as soon as someone tells me that I have an ellipse whose center is the origin, I go ahead and put a point at the origin. So there is my center at 0, 0. The next thing I would note is that they tell me what kind of major axis I have. They say that I have a vertical major axis, meaning that which side is longer, up and down or left and right? Up and down, good job. And that vertical major axis has a length of 10, which means the entire length, or 2a, you can look back at your notes if you need to, is equal to 10. In other words, a is equal to 5. So from my center, which was at 0, 0, if it's a vertical major axis, which variable am I changing as I relocate to go to my vertices? That's right, the y values. So I would say 0 goes up 5 and down 5. So if I went up 5, there's one of my vertices, and the location of that vertex is at the point 0, 5. What's another one of my vertices? Well, if I went 5 units below, 1, 2, 3, 4, and 5, there's another one of my vertices, and that's going to be at the point 0, -5. If you wanted to save time on a handwritten test, you could write 0, and then use the plus or minus symbol 5. That would work as well. One other thing to note, we have enough information to get a better sketch, don't we? Because we are given the information about the minor axis as well. We're told that the minor axis, which in this case would be going left and right, since it's not a horizontal major axis, but a vertical one, we would notice that it has a length of 6, meaning that 2b should equal 6. So b is just 3 in each direction from the center. So if I'm going left and right from the center of 0, 0, I would go left 3 units, and I'd land at an endpoint at -3, 0, and I'd go right 3 units, landing at the endpoint 3, 0. Now I could draw a basic sketch at this point. If I just wanted to draw a picture, I can do that. So I'd connect my dots to my vertices and to my endpoints that I've already put on my graph, And I could draw, it's kind of ugly, but you get the idea, a sketch of a vertical major axis ellipse. Okay? But what they've actually asked me for are the foci. So without even drawing the picture, I could have found those 2 points. Remember, the foci are going to be points which are inside of, let me grab another color that you can see, inside somewhere of the ellipse itself. So my C value should be smaller than my A value. Well, to determine that, I need to remember to get to my foci, I use C. So I'm going to take C squared and say, what did it equal again? Can you check your notes? That's right, A squared minus B squared for an ellipse. Again, you can look in the textbook for a proof of this. We don't have time to do the proof for most things in this class, unfortunately. So if we were to actually plug in what we have here, we would have that A is 5, so I'm going to take 5 and square it. Then I'm going to subtract whatever B is squared. You could do a lot of this in your head. I'm just trying to spell it out in case anyone's lost. Okay, so what do we end up with here? That's right, we get 25 minus 9, or just that C squared equals 16. Well, that must mean that we know C. You can take plus or minus the square root, but since C is a distance, you're only interested with in the positive answer. So C is the square root of 16, or just 4. Again, what does C tell you? The distance from the center to each of your foci on the major axis. So now I know that if I went up 4 units from the center, there's one of my 2 foci, and that's at the point 0, 4. And if I went 4 units below the center on the major axis, that would land me at the point 0, -4. Or in other words, 0 plus or minus 4 are the locations of my 2 foci. Okay, and so that keeps you honest. It shows how you actually check if a point is on the actual elliptical pathway by seeing if the sum of the distances to each of the foci when added up is going to remain constant for each point. Okay, so now we have found the foci, again using the letter C and the relationship between A, B, and C that we'll memorize for an ellipse. This is only for an ellipse. In our next video, when we talk hyperbolas, that minus sign will become a plus sign. So we have to pay really close attention that we know what type of conic section we're talking about. For an ellipse, that's a minus sign. Notice also to get to the vertices, we needed the letter A. And we found that by looking at the length of the major axis and cutting it in half. Okay, so we've done one example where we asked you to give us the foci and the vertices based on the description of the ellipse. Let's see if you can go a different direction. In example 2, we give you the equation of this ellipse. Now, I ask my students often in class, face-to-face students, how can you determine if an ellipse is an ellipse? By just looking at the equation. And one of the ways you can tell that it's not, for example, a parabola is because we have more than one squared term. Remember, if it's a parabola, only x is squared or only y is squared. So I know this is not a parabola because both x and y are squared. Next, I'd ask myself, is it a circle? Well, to tell if it's a circle, I would see whether these coefficients are the same and if we're being added together, right? Well, they are being added together, but the coefficients are different, which is why this, in fact, will be an ellipse. We'll learn in our next video, in our last video on conic sections very soon, we'll learn that if that's a minus sign between the squared terms, it's not an ellipse, but a hyperbola. Okay, so we know this is an ellipse because they're both squared x and y. They're added together with different coefficients. Next thing I notice is I don't have to complete the square this time because I don't have any other floating x or y terms. This time, I'm really close to standard form already. What should I do to make it perfectly in standard form? What do I need to do first? That's right, I should divide by whatever this constant is on the other side. So if I divided each of these 3 terms by 100, I would have standard form right away. So the standard form of this ellipse is what? Go ahead and pause the video and do it yourself. Let's see how you did. Did you get x squared over 25 for your first term, plus y squared over 4 as your second term, equaling 1? If so, great job. If not, what you're doing is simplifying. 4 divided by 100 is really 1 over 25, and 25 over 100 is 1 over 4. I'm just simplifying here. Keep in mind that if that had been a number like 3 over 100, you would need to put 100 over 3 as your denominator, or 100 over 4 in this case, which is 25. Okay, so there's always a way to get it in standard form if it's not obvious at first. Okay, now once we have it in standard form, can you help me determine what type of major axis we have here? In other words, is it going to be longer horizontally or longer vertically? Well, where's the bigger number? That's right. It's under the x squared term. So if it's under the x squared term, this must mean that we have a horizontal major axis, not a vertical major axis. In other words, we're going to have a longer left and right than we are up and down. Okay, how do we determine a, b, and c? Well, a squared is always the bigger number for an ellipse. So if a squared is 25, we can find that a is a distance, so it's positive square root of 25, or 5. We also would know that b squared is the smaller of the two. So b would be the square root of 4. Since b squared is 4, b is the square root of 4, which is 2. So I could already begin this sketch now, couldn't I? Where was my center at? Can you see where the center was? Yeah, it was at HK. So if there was no addition or subtraction inside parentheses there, your HK was just 0, 0. So your center was the origin again. We were being quite nice to you. Now if I wanted to go to my vertices, which are on the major axis, would I go left and right from the center, or would I go up and down this time? Well, because the bigger number was under the x, I have a horizontal major axis, so I go left and right from the center. So since the center had an x value of 0, I'll be adding and subtracting my a, so we use a to get to my vertices. I'll be adding and subtracting 5 to 0, which would mean I'd be over here to the left 5 units. So there's one of my two vertices, and to the right 5 units. There's another one of my two vertices. So my points for my vertices this time are positive and negative 5, 0. Again, this is an easy problem because I started at the center of 0, 0. Had I started anywhere else, you would take that x value and add and subtract 5 respectively. What about for my endpoints on the minor axis? So if I was interested in getting a better sketch, I would need my endpoints on the minor axis. So in other words, going up and down instead of left and right, well, that would be b units, right? So b units from my center, well, my center was at 0, 0, so I would be going up and down b units, so 2 units. That would mean going up 2 units, there's a point, at 0, 2, and down 2 units. There's a point at 0, negative 2. In other words, 0, positive, negative 2 would be the locations of my endpoints on the minor axis. And you could already draw a sketch right now. Something like this is happening. There's my semi-ellipse with the positive top half, and here's my bottom half of my semi-ellipse, of my ellipse. So I can do 2 semi-ellipses to connect and make an ellipse. Okay, finally, to keep yourself honest, you could get the foci, right, to make sure you understand what's really going on behind the scenes. So what makes this truly an elliptical pathway? The foci. And to get those foci, remember, we need the letter C. So what was that relationship between A, B, and C for an ellipse? That's right, C squared equals A squared minus B squared. So in this situation, A squared was 25, B squared was 4, 25 minus 4 is 21. So if C squared is 21, then C is the square root of 21. So that's the distance that we would travel on the major axis, left and right, to get to my foci from the center. So if you think about the square root of 16, which is 4, and the square root of 25, which is 5, the square root of 21 is somewhere in between there. So it's 4 point something. So in your graph, you could go 4 and change, right? 1, 2, 3, 4 and a little bit, and 4 and a little bit, just for an approximation. We're not trying to be an artist here. We're just trying to get a sketch. You want to make sure that that makes sense. Are your foci within the elliptical trajectory? They should always be inside or in between your vertices and your center. Okay, so let's take a look here. Our equation, or rather our points, would be the x and y values have shifted, so positive and negative square root of 21 to be exact, and the y value stayed at 0, didn't it? So we always start at the center, and then we move on the major axis to find our vertices and our foci. So we've drawn a sketch of an ellipse here. Again, I would recommend pause and try a lot of these on your own before you continue on to a different type of skill to make sure you've become an expert. Well, let's try another problem where it's not quite as obvious. In example 3 here, we're told to complete the square and rewrite the equation of this ellipse in standard form. Now, to be honest, most of the time, we're not going to be quite so nice. We're not going to say, complete the square to do this. We're just going to say, graph this, or use this equation for something. So you would have to look at this equation and be able to tell me, first of all, what type of model it is. And so by looking simply at this equation, I could determine that by paying close attention to patterns. One pattern is, I notice that I have two squared terms, x and y, so it can't be a parabola. I notice they're being added together, so it can't be a hyperbola, which we'll study in our next video. And now I say, okay, so it's either a circle or an ellipse, right, if they're both squared. Well, the coefficients are different. So this is the degenerate circle, right? This was the ellipse. So that's how I first determined that. The next thing I would need to focus in on is how would I get this into standard form? And the way that we would have done that when we talked about parabolas or other types of conic sections, even the circle, was to get from general to standard by completing the square. So you have to be able to walk yourself through that process. You're not going to have someone telling you what to do in the future when you get to calculus. So remember the first thing you did when completing the square? That's right, you move your constant to the other side. So I have 32 by itself on the right, and then you group your variables together. So the x variables get grouped together, so like 3x squared plus 12x, and then you left some space for that third term that you're going to work on creating by completing the square correctly. And then you grouped your y terms together, so I did 3x squared plus 12x. My y terms would be positive 4y squared and negative 16y, and then leave some space because you'll be completing the square there. Now, if you remember from circles or parabolas, when you completed the square at this step, you would normally just take half of b and you'd square it. But that was because you would typically be dealing with a situation like x squared plus bx, and you were looking for this magical third term that makes this a perfect square trinomial, which can become something plus something squared, right? Well, in this situation, notice we have a coefficient of 3 for x squared and a coefficient of 4 for y squared. So we can't just jump into our situation of taking half of b and squaring it and making that our third term. We can't jump right into the process of completing the square. We have to factor out our leading coefficient first, and then we can execute our algorithm here. Okay, so you first have to factor out that leading coefficient in order to begin that algorithm. So let's go ahead and do that. If you factor out the 3 for the first pair, you would get x squared plus, that's right, 4x, and then we'll leave some space. If you factored out the 4 from the next grouping, you'd have 4 times parentheses y squared minus, that's right, 4y, and leave some space for your completing the square, equaling 32. Okay. Now at this point, you are ready to use your algorithm for completing the square. So the completing the square process is now set to begin after you've taken care of those leading coefficients, factored them out. Be careful, it's going to be a little bit tricky. So when you take half of b here, half of b, in this context, b is 4, isn't it? After you factored. So that 4 gets cut in half, and half of 4 is 2, and then it's squared, and 2 squared is 4. So if normally you would just add 4 to both sides, right? Careful. What have you really done by inserting a 4 in parentheses to this equation on the left? Well, eventually, doesn't the 3 get distributed to all 3 terms? So eventually, after distributing the 3 to all 3 terms, the net effect, the ultimate outcome, is that 3 gets multiplied by 4. So the net effect by putting a 4 in parentheses is that you've really added 12. Who would have thought? So by adding 12 to the left side of the equation to maintain balance, just like in a chemistry situation, you have to maintain balance, we're going to add 12 to the right side as well. So that is a mistake students often make. So if that was something you think you're prone to do, make a note, because we usually repeat our mistakes. So we want to make sure we can practice doing that correctly a few times to override that sequencing in our brain. Let's try completing the square by yourself this time. Go ahead and do it with a negative 4 here next to the y. Pause the video, try it on your own. Okay, let's see how you did. When you took half of negative 4, you got negative 2. When you squared negative 2, did you get positive 4? That's right. So you added a positive 4 in the parentheses. But what was the net result of putting a 4 in parentheses? Well, the net result would be eventually that 4 gets multiplied by whatever's in front. So eventually you've really multiplied it by 4, which is 16. You've added a 16 on this side of the equation, which means you must also add a 16 on the right. Now you have a lot of addition to do on the right side. The collateral damage there will be your new constant that we'll be working with. And I was kind, you'll like that number if you do it correctly, I promise, okay? So take a look at what we have here. After you factor now, because you've created a perfect square trinomial which factors nicely, what factorization do we have for x squared plus 4x plus 4? That's right, x plus 2x plus 2, or x plus 2 squared. Similarly, we add the positive 4, and then we say, what is the factorization of y squared minus 4y plus 4? That's right, y minus 2 squared. And on the right side, what was the result of adding 32 plus 12 plus 16 all together? Yep, you should be getting 60. Okay, you are one step away from being in standard form. I know this problem took a long time, but this is a skill you're going to want to work on to make sure you become really, really comfortable doing this to get standard forms. What you want to do now is to get 1 on the right if it's truly an ellipse in standard form. So dividing each of your 3 terms by that number 60 will make that happen. And now we'll get our equation, and it simplifies quite nicely. Like I said, I was kind here, because 3 does go into 60 20 times. So we would have x plus 2 quantity squared over 20 plus y minus 2 quantity squared. And 4 over 60 reduces to 1 over 15, so our denominator is just 15. And 60 over 60 is just 1. We get to stop here because that's all the problem asked us for. But in a real situation, like when you go further in math, you would then use this model to either graph it or to make predictions, right? So at this point, this is our model in standard form. If I had asked you to start graphing it, you'd say, what's the center? Oh, negative 2, 2. What is a squared? The bigger number, so 20. What is b squared? The smaller number, so 15. What kind of major axis does this have? Well, the bigger number's under x squared, so horizontal. And then you'd continue finding c squared to get to your foci and get your endpoints on the minor axis and draw a sketch. So you could go much further. In fact, I've attached the link to the Desmos graph online, so you're always welcome to check your work if you'd like to go on and graph this for practice. One more problem now. We're going to do a word problem using an elliptical path. So let's take a look at our last example today. It says a bridge is built, and technically it should say a bridge is built in such a way that it is shaped on top of an arch that is semi-elliptical in nature. Okay, so this bridge is actually sitting on top of an arch which has a semi-elliptical pathway. Okay, now a lot of students will look at an arch in real life and they'll just say, oh, it looks like a parabola or it looks like an ellipse. You can't assume anything, right? You actually have to fit the equation to the model to see if it's actually that pathway. But we're told this time what kind of pathway that arch is. It's semi-elliptical. So what I'm going to do is I read this word problem. I'm not going to overreact. I'm just going to start drawing a little picture over here and writing down what we know. Okay, so that's my recommendation to you. Anytime you do a word problem, take it one piece at a time. So we're told that this bridge is shaped, well, this arch is shaped like a semi-ellipse. So one thing I would do is recognize that an arch typically looks something like this. I'm not doing the best at my art skills here, but something like that. So we have an arch, which is a semi-ellipse, meaning it's only half of an ellipse. Now, right now, we can't assume anything. It could have a horizontal major axis. That could be a possibility. Or our situation could be such that we have the longer side vertically, right? Ooh, that's rough. Our arch could be something like this with a vertical major axis. So they're not telling me that just yet. I got to keep reading. What else do we know? It says the span, and again, the span means the length that the whole thing spans from the left to the right, okay? So the span is always horizontal in nature. The span is 102 feet. Well, they've also been very kind. They've said that is the length of the major axis, haven't they? By them telling you that the span is your major axis length, well, that's really good news because now we know that from here to here is my major axis, right? This is called my span. Now, if it had been in this situation, if this had been my span, that wouldn't make sense because that would have been my minor axis. If it was a vertical major axis, that wouldn't make any sense. So we can rule out this picture since the span is always horizontal in nature and they told me that was the major axis. Okay, so what else do we know? Well, we know the length of the span. The span, which is the length of the major axis, so 2a is always the length of the major axis, has a length of 102. So don't we know what a is? Dividing 102 by 2, we would get 51, wouldn't we? So we would go 51 feet in each direction from the center. Now, I chose to put my center at the origin to keep my life easy. You could put it anywhere you like in your picture, but I like to make my life easy. So knowing that, I now have some information about this point and this point. Those points are going to have an x value of negative 51 and positive 51. And this is often the case. In a word problem, they give you data for at least one point on your path. Here, they've actually given us part of the partial data for 2 points, haven't they? They've given us the x values at these 2 locations. Let's see if they give us more information, because that's not quite enough to tell us the full story. Okay? What else do they tell me? Sentence 2. We only know one sentence. If the height of the arch, okay, got to read carefully. Now, it might be telling me the height from the center. It might be telling me the height somewhere else, because at different points, it has a different height, right? It says if the height of the arch 27 feet from the center is 12 feet above the ground. Okay, this is the part most students misread, so be really careful here. It's saying 27 feet from the center. Is that horizontal or is that vertical? 27 feet from the center. That would be horizontal, wouldn't it? So if I go out 27 feet, I should have a y value there of 12 feet above the ground. So this location is 12 feet above the ground, 27 feet from the center. In other words, they just gave me a point. When x is 27, y is 12. Most students mix those two up if they're not paying close attention, okay? Technically, they've given you 2 points if you really are paying attention. They've actually said either direction, right? So if you went 27 feet to the left, that's negative 27 for x. You would also have the same y value of 12. That's what we call a vertical clearance typically. So if you had a truck that was a certain width, you would want to make sure that its clearance was going to go under that tunnel, for example, if this was a tunnel. This is under a bridge, but you get the idea, I hope. Okay. So they usually give you some information about a point, and that's what they just did. So what they're asking me for, they say, okay, now that they told me that, the last part of the sentence is, find the height of the arch, where? At the center, and round it to 1 decimal place. So what they're really asking me for in my picture is the distance from the center to the top of this arch. That's what we're after, isn't it? So we're actually looking for a certain y value, aren't we? Now that y value has a name, right? From the center to a point on the minor axis, that is called what letter? A, B, or C? That's called B. So we are after B. We want B. So in order to find B, we need to use our model, okay? We don't have C, so we can't just plug it in. That would be really nice if we knew the distance of the foci. Some students misunderstand the problem, and they think that 27 is C. No, 27 is a specific location on the trajectory of this arch, of this semi-elliptical path. So what we are going to have to do is look at the equation that describes the full ellipse, and then use that equation and the points that are given in order to find B. So let's do that. If you have a horizontal major axis, which we were given because that was our span, they told us, what variable, x squared or y squared, assuming we're at the center, so it's something like this, what variable, underneath which variable I should say, is your bigger number? Would it be under the x squared or the y squared? That's right, it would be under the x squared. So here would be our a squared and here would be our b squared, and we would be equal to 1. This is my elliptical model. So we think, what is the model for an ellipse? That would be the model because its origin was the center according to the way we drew the picture. What else can I put in my equation? Well, I now know what A is. A is 51. So my model could become x squared over 51 squared plus y squared over b squared equals 1. So if you're looking at your model and you're pretty proud of yourself, that's great. You do have a model that describes the full ellipse, okay? And then you could just solve for y and make it the positive, and you have your semi-ellipse if you're interested in just that half. But in this situation, we weren't after that, the formula. We were after b. So how would I find b using the information that's been provided? Well, they gave me a point, didn't they? They told me that there were actually 2 points on this graph, and those 2 points on that graph were 2712 and negative 2712. Technically, the point at 51 and negative 51 had y values of 0, so I could finish those points as well if I wanted to. Okay, but as far as using the other 2 points, we could pick whichever point we like. I usually do the positive version. It doesn't matter because you're squaring both x and y, aren't you? So if you put in either positive or negative 27, I'll do the positive. So 27 squared over 51 squared, and then y was 12, so 12 squared over b squared. B is the unknown, we don't know. We would now need to solve using basic algebra. It doesn't feel very basic, but this is still basic algebra for b squared. And so when you square these numbers, let me look at my handy-dandy notebook here because I did this with my calculator earlier for you. We should be getting 729 for 27 squared. For 51 squared, we get 2,601. We know 12 squared is 144. And b squared is the unknown equal to 1. So how do you go about solving an equation which has fractions? A few options, right? You could either clear the fractions by multiplying all 3 terms by 2601b squared, your LCD. My preference is to move the fraction 729 over 2601 to the other side by subtracting it and then cross multiply. But you can use any of those methods. So if you had done the method I like, I subtract this fraction from both sides. I would get 144 over b squared. Then I would get 1 minus this fraction. The new numerator you get when you take 2601 minus 729 is 1872 over 2601. That was just subtraction. Then I can cross multiply, and if you cross multiply, you'll get 1872 next to b squared. You'll get 144 next to 2601. I can't fit it there, but that's 2601. When you multiply that out, you would then divide that answer by 1872, and your b squared should be something like 200.07, something thereabouts. I've rounded it at that point. The defined b, you can take the square root, and I rounded there as well to 1 decimal as I was asked to, and I got 14.1, roughly. Let's see if that makes sense, and this was in feet. Where is b? B is the distance from the center to the top of my semi-elliptical arch. So does 14.1 make sense? Well, what do I mean by make sense? If this is truly an elliptical pathway, A should be bigger than B. And A was 51 and B is 14. So this is making sense as far as, is it even possible? If you had an answer for B like 55, wouldn't make any sense because A was on the major axis and it should be bigger than B. Okay, so at least that part is making sense. You could also now, if you had time, plug in the points that you were given into this new model with your new B that you found. You could definitely plug that in and see if your points are in fact truly on this model by plugging them in and seeing if both sides are the same. So that is a way to check yourself. But as far as answering the question, we've done it. We found B, the distance from the center to the top of this semi-elliptical arch. Okay. We've done a lot today on this video, so I really encourage you to make sure you practice on your own because math is not a spectator sport, and next time we'll finish conic sections with the hyperbola. See you then.